Okay, so 1, 2, 3, 4, 5. Okay, output should be 5. Yeah. So you can just no, re-execute. Yeah, I just updated to 5, so you can just try it. Okay, so yeah, using pivot element, right? So what is happening in this diagram? So quickly we'll see what is the quicksort technique using Hover's partition scheme, right? So the name of the algorithm provider is Hovers. The name of the author is Hovers, right? So basically we assume the first element as pivot and we have two indexes, right? Left and right, or you can say I and j. This is our low pointer. This is our high pointer, correct? Then this will be initially I and this will be j. So we compare the next element a of I with pivot we compare. If it is less, we will increment I less than or equal to. So we'll increment I. Otherwise, we'll check if the a of j is greater than pivot. So both the pointers we move, at the same time. So we can also call it as two pointer approach. So I and j will be simultaneously moving from both ends. So if the a of I, that is a of low, pivot, if it is less than or equal to the pivot, we will increment the I. So in this case, what is happening? So 7 is less than equal to 7, condition is true, we will increment I. So I will come here. Then again, 6 is less than 7, condition is true, I will come here, right? Now 10 is not less than 7, so the condition is false. So we will check the pointer from the back end, that is from the highest pointer. So here we'll check whether a of j is greater than the pivot. So in this case, 7. So 7 is not greater than 7. This condition is also false, right? So once both the conditions are false, what we will do? We will exchange. What we will exchange I and j values, right? So a of I and a of j. So what will happen now? So your current uh, array will be 7, 6, 7, 5, 9, 2, 1, 15, 10. So you should able to understand that. So let's take one diagram and do it neatly so that you will recollect what is happening. So what is your input array? 7, 6, 10, 5, 9, 2, 1, 15, 7. Okay, 7, 6, 10, 5, 9. In 7, right? So this is your initial array. So this is our pivot and this is our I. This is our j, correct? So we compare a of I with pivot. So if it is less, we'll increment I. We will increment I. In this case, it is not less than 7. So we'll check a of j. So a of j is not greater than pivot. So this condition is also false. So we'll exchange element at the position I and j, right? That is the technique. So at this point, what will happen? So your or array will be 7, 6, 7, 5, 9, 2, 1, 15, 10. I and j will be there only, right? So your I and j will be there only. Then we'll keep on looping again as long as we are within the range of low to high, right? So as long as we are within the range of low to high, we have to keep on doing this process. Okay, so now same thing we will do. Now you see 7 is again less than pivot 7. So we'll increment I. 5 is less than 7. We'll increment I. But 9 is not less than 7. So we have to check the condition j here. So here 10 is greater than 7. Condition is true. So we have to decrement j. 15 is greater than 7, condition is true, we have to decrement j. But 1 is not greater than 7, so we won't exchange. Now at this point, what we will do, we have to exchange the element present at I and j. So we have to exchange 9 and 1, correct? So when we exchange 9 and 1, what will happen? 7, 6, 7, 5, 1, 2, 9, 15 and 10, right? So your I and j position remain same. So this is your I, this is your j. Now we have to keep on continuing the process. So 1 is less than 7, condition is true, we have to increment I. 2 is less than 7, condition is true, we have to increment I. But 9 is not less than 7, so we have to check the j condition. So here 9 is greater than 7, condition is true, so we have to decrement j. So j was here, now it will come to 2's position. Now 2 is not greater than 7, condition is false, right? So 2 is not greater than 7, condition is false. So we have to check whether I is less than j. So in this case, you see I pointer is greater than j. So obviously I is not less than j. So at this point, what element we have to exchange? When I becomes greater than j, we have to stop the entire iteration and we have to split the array into two halves based on j's position. So here what element we have to exchange? We have to exchange a of j with a of low. What is our a of low? 7. What is our a of j? 2. So when we exchange a of low with a of j, so our output will be what? 2, 6, 7, 5, 1, 7, 9, 15 and 10. Correct. So we get this output. And what is our j here? So after this, what we have to do? We got the exact mid position. That means this is our midpoint now. Correct. So we have to sort all these elements separately. Right. So 2, 6, 7, 5, 1 we have to sort separately, and 9, 5, 15, 10 we have to sort separately. Correct. So again, for this, what we have to do, same approach we have to follow. This will become our pivot. This is our j. This is our I. Then we'll compare a of I with a of low. So condition is true, I will be incremented. Now a of I is not less than 2, condition is false. So we will check with j. A of j is also not greater than 2, condition is false. So we have to exchange a of I with a of j. Correct. So here what will happen after exchanging? 1, 6, 7, 5, 2. So our you have to exchange a of I with a of j. That means 2, 1, 7, 5, 6. Your I and j pointer will be there only. Then you will have to continue doing the same process. So here 1 is less than 2, condition is true, so we have to increment I. 7 is not less than 2, condition is false, so we have to check this j pointer. So here a of j is greater than 2, condition is true, so we have to decrement j. A of j is greater than 2, we have to decrement j. A of j is greater than 2, so condition is true, we have to decrement j. Now at this point, 1 is not greater than 2, condition is false. So we have to check whether I is less than j. In this case, I is not less than j. So what we have to do? Again, exchange a of j with a of pivot. So that means 1 will come here, 2 will come here, 7, 5, 6. That means what we have done, we have sorted left side separately and right side separately. Correct. That means this is our mid position now. This is our mid position. Now again, we have to sort this part separately and this part separately. Since there is only one element, no need to sort. That means it is already in its correct position. Now the same process we have to apply for 7, 5, 6. So in that way, you have to keep on continuing the quick sort based on 2 pointers. So hope you got some idea based on whatever the hint I have given. Now based on this understanding, can you complete the loop? So have I got the correct output here? Okay, somewhere I went wrong here, right? So maybe 7th position, we made some mistake. But can you just redo it and see whether you are getting the same kind of tree? So this is called as recursion tree. So this is our splitting point. So we have to sort this element separately and this element separately, right? So can you just check it out where we made mistake? So I think in my diagram, we got 7 here only. It's supposed to be here actually. Right, so this is I, J. So we have to exchange A of I with A of J. Sorry, this is I. So that means 7 and 10 we will exchange. So this becomes 7, this becomes 10. No, 7 is less than 7, I will come here. 5 is less than 7, I will come here. But 9 is not less than 7. So we will check A of J. So again, A of J is not less than 7. So we have to exchange 9 with 7. Yeah, so I think this part we have missed. So here 7 is not greater than 7. So we have to exchange this 9 with 7. That means 7 will come here and 9 will go here, right? I'm sorry, sir. So here 10 is greater than 7. Condition will be true. So we will decrement J. 15 is greater than 7. Condition will be true. We will decrement J. 1 is not greater than 7. So condition is false. So we have to exchange 1 with 7, right? So 1 will come here, 7 will go here. So in that way, we have to do the partitioning. So hope you have like some kind of idea based on whatever you already learned. So can you try to trace it and see whether you're getting the same kind of manually how to do this, because you can't by heart this technique. You have to try in the book and see where exactly the partition is happening, right? So this is the partitioning point, and based on this partition, left side of that we have to sort separately, right side of that we have to sort separately, and for this again same condition we have to apply. So this will become my pivot, right? So you can just verify here. So I will come here, J will be here. So 7 is greater than 2, J will be decremented. 5 is greater than 2, J will be decremented. But 1 is not greater than 2. So condition is false. So we have to exchange I with J. That means 1 will come here, 6 will come here, right? Similarly, again, 1 is greater than less than 1, less than or equal to 1. Condition is true. So I will come here. J will also be here only. But 6 is not less than 1, right? So condition is false. We will check whether J is greater than 1. So A of J is 6, which is greater than 1. Condition is true. So we will decrement. Then 1 is not greater than 1. Condition is false. So we have to exchange A of J with A of low. So that means 1 will be exchanged with 2. That's why these two are swapped here. Correct? These two are swapped. So that's why left side there is only one element. So there is no need to further split the array. But right side we have to still split it, because as long as there are more than one element, we have to keep on doing this recursion, right? So 657, again, we have to apply the same partition scheme until we reach the single element. So once we reach the single element, so you can see this is sorted. So wherever pivot is highlighted in the green color, that means it is already in its correct sorted position. So after 1, which is coming 2. So after 2, next you have 5. So after 5, we have 6, then 6 and 7, right? Then again, one more 7 here, 7, 10. 10 is a partitioning point, right? Not 10. So here, 9, 10, and 15. So in that order, the recursion will be merging the elements, right? So this is the basic scheme what we might have already learned. So I'm just revising this. Okay, so this partition scheme is called as a Hoover's partition scheme, which is the most efficient among all the techniques that we have. So there are multiple approaches. So this is the basic one which I have explained. So let's see how to do this in Python. So any doubts you have in this? Anyone wants explanation still? How it works? So I hope you understood what we have done on the screen. Basically, we are comparing the element from both the end, left and right. So we have to keep on doing that process until the array is sorted. I think instead of 657, I got 756. So here there was some mistake, but I hope you can just try to trace it properly. Okay. So what is next thing is how to implement this in Python, right? So next we have to concentrate on the implementation. So implementation wise, whatever the approach you have followed for the C language, same you can use, but with some changes will be there in terms of swapping and all, but remaining part will be same. So let's call the function name as quicksort, right? So quicksort here obviously takes three inputs. One is array, and one is low pointer, and another is high pointer. So low will point to the 0th index, high will point to the n minus 1th index, correct? So initially we will just keep it as parse. Let's try to read the input from the user. Okay, so let's say I want to read the input from the user, space separated value. Okay, then we will call that quicksort function with the array. And what is our starting element? Should be position is 0. And I have to pass the size of array minus 1. So for that, I have to find length of array, then minus 1. So we have to pass this data to the function. Then finally, we'll print that array. Correct. So this is the reading part. Now, what is the logic here is two pointers, as I told you. So you have to keep on doing this process as long as this you are within the boundary of the array, right? Suppose say your low pointer is here and your high pointer is here, correct? So suppose if your low pointer is greater than high, correct? If low pointer is greater than high means obviously you can't sort it. It has to be within the boundary of the array. So always low should be less than high, then only you are going to sort it. So when the low becomes greater than high, that means you need not to sort. That means the array is already sorted or you are having left with only one element. So that is the first condition you have to check whether you are within the boundary of the quick sort or not. Right. So first condition is if low is less than high. Right. So only if the low is less than high, we have to keep on doing that. Otherwise, we have to stop the process. So tell me next what we have to do. So we are assuming that we are considering the first pivot element, considering the first element as pivot. Okay. So how to consider the first element as pivot? So let's say pivot equal to what I should declare a of low. Why low? Because low is pointing to the 0th element. So pivot will become my first element, which is a of low. So 0th index element will become pivot. Okay. Then after that, we need two pointers, right? I and j. So I should be initially pointing to low and j should be pointing to high. That's what I explained in the diagram. So I should be pointing to low pointer, j should be pointing to the high value. Then this comparison process we have to keep on doing as long as I is less than j, correct? So once I becomes greater than j, that means again you don't have sufficient elements to sort, so you have to stop the process, right? So until I is less than j, you have to keep on doing this process, right? Then inside this condition, there are few more conditions that you need to use. So while I is less than equal to high, this is very important point because suppose say for example the array is 5431 and you are moving I value something like this. At certain stage, your I value went beyond high, correct? That means you have exceeded the array boundary. That means you have to stop the iteration and just exchange a of I with a of low, a of j with a of low, correct? So we have to make sure this I is within the boundary of this high. Okay, so that's why the condition should be I is less than equal to high. That is the first condition. Along with that, we have to check whether a of I is less than or equal to pivot. That's what we were doing, right? So like in the diagram, we were comparing whether this a of I is less than pivot. So initially pivot is also same, position is also same, and a of I is also same. So obviously you are comparing 7 with 7 only, condition will be true. So I will be incremented. Okay, so if this both the conditions are true means what we have to do? We have to do I equal to I plus 1. I pointer will move. Suppose this above condition is false, we have to check with the reverse, starting from the back end where we are moving the j pointer. So here what is the condition? If a of j is greater than pivot, right? So if a of j is greater than pivot, we have to decrement j equal to j minus 1. So these are the main foundations of the quicksort, right? So you are comparing the AH element with the pivot. Less than means increment I pointer. If it is false means check with the backend. If A of j is greater than pivot, decrement the j pointer. So after this, suppose if both the conditions are true, I mean both the conditions are false, what you have to do? We have to check if I is within the range of j. So if I is less than j, what we have to do? Swap A of I and A of j, right? So how will you swap A of I and A of j in Python? Generally swapping, what you do? You use temporary variable, right? So in Python, how can I swap directly in the same line? Anyone? How can I swap A of I and A of j? Yeah. So like we just said, this is the correct statement. So you can directly use this statement. So A of I should be swapped with A of j means you can write like this, one single line. So here, what is the meaning? This j will go into I, this I will go into j, right? So if I is less than j, we have to swap A of I and A of j. Suppose if I is less than j, this condition is false. That means we have no, completed all the possibilities. So we have come to the partition point. So we have to come out of this main loop. Once this condition is false, we have to come out of this inner loops to main loop. And at this point, what we have to do? We have to exchange A of low with A of j, correct? So A of low comma A of j equal to A of j comma A of low. That means we are exchanging that midpoint element with the A of low, right? Then after this, what we have to do? Tell me. So once we have done with this, so now we have got this j pointer means, so this is jth position, right? So say for example 0, 1, 2, 3, 4, 5. So jth position is 5. That means we have to sort all the elements from 0 to 5 minus 1. That means 0 to 4 we have to sort separately. Then j plus 1 to high. So j plus 1 means 6 to 6, 7, 8. So we have to sort this part separately and this part separately again. So for that, what is the index I have to pass? I have to pass A of, I have to pass j minus 1, 0 to j minus 1 and j plus 1 to high. We have to call recursively the same quicksort function again. We have to call the same function again with the updated pointer. So what we will do, we will call the quicksort again with the A as the array which we need to sort. So A of A comma low to j minus 1, which will sort the left portion. Then again quick sort A comma j plus 1 to high. Why j plus 1 to high? This will sort the right side of the array. Okay, based on the mid pointer, which is j. Right. So like this, if you keep on doing, you will get the sorted output. Okay, so let's see whether it works or not. So say for example, I'm entering the array as 5, 4, 3, 1. Right. So we are getting the sorted array 1, 3, 4, 5. And enter any other number. Right. So everything is coming as a sorted value. So 2, 3, 3, 4, 4, 5, 5, 6. So it is a sorted value. So can you just try to trace with 5, 4, 3, 1? So take some basic example 5, 4, 3, 1. So it's a simple to understand, right? So tell me, so 5, 4, 3, 1. So what is happening here? This is our pivot. This is J. This is our I. So initially, I is less than I, condition is true. I is less than J, condition is true. And A of I is less than pivot, that is also true. So what we have to do, increment I. So I will come here. Now next value is 4. So 4 is less than equal to 5, condition is true. I will be updated. 3 is less than 5, condition is true. I will be updated. 1 is less than 5, condition is true. I will be updated. So what happens at this point? Tell me which condition will become false. So our 0, 1, 2, 3. So I went out of the boundary from high, right? So at this point, this condition becomes false. Correct or not? This condition becomes false. While I is less than equal to high and A of I is less than equal to pivot, I equal to I plus 1, this condition becomes false. So what we have to do, we have to check for whether A of j is greater than pivot. Correct? So what is our A of j? A of j is 1. So 1 is not greater than pivot. Even this condition is false. Now we have to check if I is less than j. So see, already I went out of the boundary. So it is obviously greater than j. So this condition is also false. So all the conditions are false. So what condition will be executed? This will be executed. So we have to exchange what? A of low with A of j. So what we are exchanging? 1, 4, 3, 5. Now what does it mean? So we got a mid pointer, partition pointer is j. That means I have to sort this part separately and all the elements towards left side, right side of the pie separately, but there are no elements. So only I am left with this 1, 4, 3. Then again, same process I have to return. I have to do. So this will become my low pointer. This will become my j. This will become my I. So I will be this. 4 is not less than 1. Condition false. We will check reverse side. So 3 is greater than 1. J will be decremented. So J will come here. 4 is greater than 1. J will come here. 1 is not greater than 1. So this condition becomes false, right? Next, what we are checking if I is less than j. So obviously I is greater than j. This condition is also false. Then we'll exchange a of low with a of j. That means we are exchanging 1 with 1 itself, correct? So that means 1 will stay in its original position only. So we have to sort out left side of the 1 separately and right side of the 1 separately. That means we have to sort now this 4, 3. So once we complete doing all the sorting, so final output obviously will get 1, 3, 4, 5. Correct? So this is how the sorting should be done in Quicksort. Now, in your model, I have given one test case. Okay, so you can do it after the session. So please observe carefully. What is the, okay, I'll just copy this one. Okay, so what you are understanding here? Can anyone tell me? 5431 is the only input I've got. I have included, but I want different outputs after each recursion call. So anyone tell me what is this output suggesting you? We are printing some extra values. What does this pass values tells you? So first we are getting 1435. Next we are getting 143. Next we are getting 34. Then again 1345. Final sorted array as 1345. Okay, here basically you need not to write this 1345. Final sorted arrays. Okay, let it be as it is as of now. Okay. So what we are doing after each iteration, we have to print the like after each splitting point, we have to print what is the array value up to that particular partition. See, when we exchanged 1 with 5, what was our output? 1435, correct? Then the remaining elements were 143. In this case, we exchanged 1 with 1 only, so we are getting the same output as 143. Then we are sorting this 4, 3 separately. So after this iteration, we are getting 3, 4 as the output. So finally, 1, 3, 4, 5 is our sorted output. So we have to print pass output after each iteration or each splitting point, right? So for that, what is the changes you have to do here? Because this is like generally it will give only single output, right? So generally what people will do for quick sort also, they will write bubble sort and they will escape, correct? So to overcome that, in a lot of online compilers, they will give the passes. You have to print the passes, right? So how to overcome this problem? Where we have to print the passes? So after you exchange A of low with A of j, we have to print the passes, right? Because this is our splitting point. So once we exchange A of low with A of j, before going to this A of low j minus 1 and A of j plus 1 to high, here we have to print the pass output. Yeah, so very good. So here we have to call some print array function. So say, for example, I am having some print array function for which I'll pass the array. I will pass the starting pointer low and I will pass the ending pointer high plus 1. Why high plus 1? Because up to that point we are we have to print, right? Including that last number also we have to print. So that's why I'm passing high plus 1. So this is the function call we are doing. Then that function you can do it outside def print array a comma low comma n, right? So whatever we have passed here, that will come and store in this three variables. So here what we have to do for I in a range of so low to n, right? So whatever the index we have passed from low up to that point, particular point. So we have to print a of I and end with space. Then for next iteration, we have to give new line, right? Okay. So what is output you're getting? 1435, 14334. So this is a very important updation which you need to know. So not just printing the final output, we have to print the pass output after each splitting point. So this is our splitting point. Immediately after that, we have to print the array up to that point, then go for the recursion, quicksort recursion. Again, once again, you have to keep on doing that. But for every recursion, this print array will be a recursion call. This print array will be printed simultaneously, right? So this is our print array, which is going to print from that particular point low to I plus 1. Okay, I plus 1, you understood why I've used. Suppose what will happen if I use I only. So last element is skipped, right? So we have to include the last element. So you have to make sure that you are passing the I plus 1. Since we are printing, we have to include I plus 1. In this case, here we are only passing I because until that only we have to iterate. We can't go out of boundary of that particular last index. So here, since we are printing the element, we have to include the last element. So this is the overall logic using two pointers, right? So it is the most efficient one. So whatever the approach you might have learned, you should always use this particular approach only because this is the most efficient, and even the number of passes swapping also is very less compared to the other approaches. So in your mind, you should always think about this logic only. So no need to know any other logic. But I will give you one more easiest way in Python. How can we do? But even though that might work, you can always use this particular approach only. So I will give you one more approach, which is also called as okay. So the name is Low-Moto partition scheme. So this particular approach, people use it for like smaller data sets, whereas like for larger set of array elements, this is the main approach. So what is this Low-Moto partition key scheme? So here, how many variables we are using for the iteration? Two, right? So I and j. So I is moving in the forward direction, j is moving in the reverse direction. And whenever I is becomes greater than j, we will exchange a of j with a of low, or else we just swap I and j, right? That's how the basic quicksort which you know. But here, the advantage with this approach is it is very simple compared to the previous one. Here, a lot of comparisons, a lot of iterations we have to do, right? So this you can avoid using Low-Moto partition scheme. So I'll just give you the hint diagrammatically, so you can try to implement it based on your interest. But since it is not necessary, so I am not going to explain in detail, but I'll give you the logic, right? So what you have to do in this approach is, so take some examples. So take a simple array, small array, 5, 4, 3, 1. So you can observe carefully and try to implement it by yourself later on. Okay, so 5, 4, 3, 1 is my input array. So here, sometimes they will ask, take the, last element as pivot. Okay. So they will say last element as pivot. So in this particular low-motor partition scheme, we are assuming that this last element is pivot. Okay. This is our pivot, right? Now, what is the logic here is your I will start from low. That means 0. So your I will start from 0th position. That is low pointer. So pivot is array of high, which is this one. And your I will be starting from 0th position. So we will start with the for loop. We will go from low to high, right? So we will use for loop for this. Okay. So your J will start from low to high, right? So inside what we have to do? So we will compare this array of J. So it initially array of J is also this low only because we are starting with low. We will compare array of J whether it is less than pivot. So what is our array of J? This is our array, right? So array of J is 5 and array of pivot is 1. Right. So obviously 5 is not less than 1. Condition is false. Right. So we have to keep on checking. So your J will be incremented now. I will be there only. So J will be incremented. So whenever array of J is less than pivot, we have to swap I and J and increment I plus plus. So in this case, since array of J is not less than pivot, so we are not going to increment I, only J will be incremented. So J will come to 4th position. So now array of J is what? 4. So again, 4 is not less than pivot. This condition is also false. So we just increment the J. Now 3 is not less than 1. Condition is false. So we will increment the J. Now, what happens at this point? Same thing. One array of J is also 1 and array of pivot is also 1. So 1 is not less than 1. This condition is also false. So we didn't update I value. So I value stays in the 0th position only. So after this, obviously, we reach the high pointer, right? So we have to stop our iteration. At this point, what we have to do? We have to exchange array of I with array of high, right? What is our array of high? Array of I is 5, right? This we have to exchange with array of high. So what is our array of high? 1. So that means 1, 4, 3, 5. Correct? So that is what you need to update. So after this, whatever the I pointer you have, that will become your partition pointer. So our I was here, right? So I was in the 0th position only. That means 1 is sorted. So left side of the one you have to sort separately and right side of the one you have to sort separately. So in this case, 1 is already in its correct position. So the same logic you have to apply for 435. So now for 435, what again we have to assume? This is our high pointer. I mean pivot pointer, pivot equal to array of high. And this is our I and J. Both will be pointing to 0th element initially. Then we have to check if 4 is less than 5, correct? So array of J is less than array of 5. I mean the pivot condition is true. So we have to increment both I and J. Right, before first we have to exchange array of I and J. Then you have to increment I. So see here. Okay, so in this case, what is your array of J? Array of J is 4 and your pivot is 5. So 4 is less than 5. So what you have to do, exchange array of 5 with array of J only. That means 4 will be exchanged with 4 only. Then the pointer will be moved. So say for example, pointer I will come here, then J will come here. Now similarly, 3 is less than 5. Condition is true. Both I and J will be moved to the next pointer. Now at this point, array of J is not less than pivot, right? The condition will be false. So we reach the dead end. Then what we have to do at this point, exchange array of I with we have to exchange array of I with again array of high only. So that means 5 will be exchanged with 5 only. So that means it stays in its position. That means there is no need to update this because it's already in its correct sorted position. That means this is our partition point now, which is I. That means right side of the I we have to sort separately, left side of the I we have to sort separately. So the same logic we have to apply for this part of the array now. So in that way, what is the change in this logic is both I and j are moving from the one position only, right? That is from left side to right side. Both are going in the same direction. But unlike the first scheme where both I and j were moving from the both the ends, I was going in the forward direction, whereas j was going in the reverse direction. In this scheme, I and j both are going in the same direction. So obviously the number of comparisons will be more in this scheme, right? Because both are going in the same direction. So that's why people for larger data set they don't use this scheme. But for smaller data set, this technique is much easier because your like number of conditions are less, number of comparisons are less, right? So those who are interested can explore this, right? It's not like mandatory to learn, but you can try to do it. So say for example, I will give some number which you can trace. So for next 5 minutes, just try to trace this input. One, 3, 4, 6, 5, 2, 1. Okay. So can you guys try to trace the logic which I've given for this input? So tell me, you need to tell me where is the splitting point and what once we reach the splitting point, what is the status of the array at up to that particular point? After all the swapping and comparison, what will be the status of the array? So I told you two things. We have to consider the last element as pivot, right? I and j will start from first element, right? What is the condition we have to check? Whether a of j is less than equal to, sorry, not less than equal to, less than. Whether a of j is less than pivot. That is what you have to check. So if this condition is true, we have to swap a of I with j, a of I with a of j, and increment I plus equal to 1. If this condition is false, so we have to just keep on iterating and just increment j value. So your j goes from low to high, right? So j goes from low position to high position. So if the overall all the conditions are false, means once your j reaches high position, what you have to do? Swap array of I with array of high. So this is just reverse of normal sorting, right? So in this normal sorting, what we used to do, we used to swap array of j with array of low, but here we need to swap array of I with array of high, right? I mean high means the last element, wherever the high position is, that we have to swap. Okay, so you can take this input and anyone tell me what is the first splitting point. Try to trace this for next 2 to 3 minutes and tell me what is the first splitting point. Actually, the smart board, I am not having smart board right now, so that's why writing is a bit, clumsy. But I hope you can at least follow. I'm trying to draw with the mouse only. So what is the first splitting point based on this technique? You should understand why we are swapping a of I with a of j. So there will be situations where your I pointer will get stuck here. Your j pointer might be coming here, right? For example. So in this case, what we need to do, we have to swap a of I with a of j, then continue the iteration, right? So most of the times, both I and j will move together. But whenever the array is like a different test cases scenario, there might be a situation where I will be not incremented, whereas I will be incremented for some elements, but j will get goes ahead. So in that situation, so we have to exchange a of I with a of j, so that they get positioned into their correct order. So this swapping is compulsory. After swapping, we have to increment I to keep iterating from the next position. So 13446521. That is our input. Okay, so anyone got the what is the splitting point? This is our I and j. This is our pivot, and this itself is our high pointer. So initially a of j is not less than pivot, correct? So a of j is 1, pivot is 1, so it is not less. So we should not increment I. We should just increment j. Then again, a of j is not less than pivot. Just increment j, increment j. So you see until last position, you are keep on incrementing. Then you reach the dead end. At this point, what you have to do, we have to exchange a of I with a of I. That means one will be exchanged with one only. So that means this one will come here and this one will go there. So you remember the point yesterday I told you, quicksort is not stable algorithm. What do you mean by stable algorithm? Can anyone tell me? So this is our I position. This is our j position. That means we unnecessarily exchanged one with one only. That's why quicksort is unstable. Unstable means when the elements in their natural order are unnecessarily rearranged, right? So that's why same element, though they are like in the correct position, they are unnecessarily exchanged, right? So now this one exchange with this one. Now this is our splitting point. So left side of this we have to sort separately, and right side of this we have to sort separately. So in this case, again, this will become our starting point, I and j. This is our pivot. We have to keep on checking. So j will be here. Same thing happens, right? So 3 is not less than pivot. So again, we will come here, j. So we exchange a of I with a of I, right? So that means 3 will be exchanged with 1. So 1 will come here, 4, 4, 6, 5, 2, 3. Now again, left side of this we have to sort separately, right side of this we have to sort separately. So hope you are understanding how the elements are getting sorted based on the iterations, correct? Then same process. This is our starting point. This is our pivot. So same thing. In this case, what happens is this is our I and j. This is our pivot. So only j will be moving up to here. At this point, you see, phi is not less than pivot. We'll move the j, but 2 is less than 3. So in this case, 2 is less than 3, condition is true. So we have to move the j pointer, sorry, the I pointer. So I is pointing to this 4, right? So our I will come here now. Before incrementing I, what we have to do, if the condition is true, we have to exchange a of array of I with array of j. That means what is our array of I now? I is here, right? So we have to exchange this 2 with 4. So that means 2 will come here and this 4 will go here, right? So that means we have exchanged the I with j. So this is what I was explaining. So when condition is true, you have to swap I with j, then increment I, right? So now condition is true. So we have first swapped 2 with 4, then we have to increment I. So I will come here, j will stay here. Then again, we have to continue the process. So here a of j is not less than pivot. Condition is false. We will come here. So j will reach the dead end. So we will stop the iteration. Now what we have to do, this is our pivot point, partition point. So left side of this we have to sort separately, and right side of this we have to sort separately. So if you observe, until here all the elements are getting sorted. So one got sorted here, one got sorted here, two got sorted here. Right. So now the same process we have to keep on doing for the remaining elements. So 4, 6, 5, 4, 3. So if you keep on doing it, definitely you will get the correct answer based on the given partition scheme. So try to implement this logic on yourself by exploring what is the complete algorithm. Definitely you will understand. So this is the quick sort using low partition scheme, but less efficient compared to previous scheme, but easy to implement. So for suitable for smaller data set. Okay. So apart from this, I'll give one more technique using list comprehension, which you can use it if the time complexity or number of swaps is not mandatory. So you can use this array. This is most easiest way in Python how to do it. So we have to do it with the recursion. So base case is obviously very important. So for anything, base case is very important. Here, what is our base case for the quick sort? Our base case is if low is less than high. So once low becomes greater than high, that means we reach the base case of the recursion. That means we have to stop the division. So similarly, for this condition, we have to check if the length of array is less than or equal to 1. Okay. Then we will return that array. Okay. Otherwise, we have to do some other process, which we have to find is a of length of a by 2. So what we are trying to find here? First, we will find the length of array and we will divide by 2. And that element itself, we are considering it as a pivot. For example, 5, 4, 3, 2, 1. So length of array is what? 5. So 5 by 2 is 2.5. That means 2, if we consider, 3 will become our pivot element. So in this case, we are considering the mid element as pivot element. So you should know what they're asking for, like if they're asking mid element or last element or first element. So in this case, our mid element becomes pivot. Then we have to sort out the left and right side of the array by saying which elements are greater than mid and which elements are lesser than mid. So left, we have to use list comprehension for this, right? So for I in A, if I is less than pivot. So what is happening here in this case? Using list comprehension, we are separating all the elements that are less than pivot goes towards left side. Similarly, for I in A, if I equal to pivot, right? Sorry, not left, mid element. So if it is exactly equal to the pivot, we were calling it as a mid element. Then which are greater than pivot, they will go to the right side. So I for I in A, if I is greater than pivot. So here all the elements that are greater than pivot will go to the right side. Okay. So after this, what we have to do? We have to just call the quicksort function with the left part of the array. Then whatever the mid we got, we have to combine it together. Then again call the right side of the array. So based on these 4 statements only, you are going to get the sorted data. Okay, quick sort takes one push. Okay, here I have to just pass the array. What is the error we are getting? Type error. Can only calculate list with list. No, we are not storing. We just have to keep sorting. Yeah, sorry. Here we have to return. So it's not sorting. No need to store actually. So this is like a shortest way which like will work, but we need to know where is the error. So don't we store anywhere? I mean, yeah, that's what I applied return, but sorting is not happening out. So I for I in a 5 is less than pivot. Okay, just try it. This technique is like a shortcut one, but sometimes we should know where is the mistake. So basically sorting is happening, but it's not printing the output. 4632. Okay, yeah. Correct. Sorry. Here you have to store it in result, right? So I missed this part only. Yeah, sorry. So hope yeah, good to you that find out when I push along. So basically I was printing that A only, right? So you have to store that return value somewhere. So I was just concentrating on this part. So that's why we always tend to ignore the small things that we do errors, because here say I was confident that I am calling properly, but we are not focusing on this. We are only focusing on this logic. So that mistake you should not do. If there is some mistake, you have to look into the all part of the code. So this is generally programmers will face this problem. Generally, if they think that okay, my code is correct, means only they'll concentrate on that part where they are going wrong. But this is a very silly mistake, right? So we are returning the value, it has to be stored somewhere. And obviously, return value means we have to either call it inside the print or store it somewhere. So this is working, right? So can you understand how it is working basically? So 5, 4, or you can say 4632 is our input, right? So what is our pivot value? Pivot value is 3. So what we are doing, left array we are creating. So this is left array, how we are creating? Left array will have all the values which are less than pivot. Okay. So that means in the array, overall array, 2, 2, right? So only 2 will be in the left part, and the right part, what will be there in the right part? All the elements that are greater than the pivot. That means 4 and 6 will be there in the right part. And in the middle part, 3 will be there because it is equal to the pivot. So once we call the recursive function, we have to call left part separately and right part separately. So how many elements are there in the left part? Only one element is there. So whenever there is only one element, we have to just return it as it is. So here 2 will be the output that we are getting. Then mid element we already have, which is concatenation we are doing, right? Plus mid means we are not adding, list concatenation we are doing. So 2 plus mid means it will become 2 comma 3. Then after this right part we are sorting. So how many elements are there in right part? 2 elements are there. So that is 4 and 6. So again 4 and 6 you will divide by 2. You will get the pivot as 6, right? So you will create left part and right part and mid part separately. Left part will go to left side, right part will go to right side. Since there are no elements on the right side, you will stop there. Left part there is one element which is 4. You will again call it and you will return that. And mid part is 6. So 2 plus 3, left part is 4. Again, mid part is 6, right part there is nothing. So we are getting the sorted output. So this is a very simplest approach. If there is no requirement of any particular partition scheme, within 5 lines, you can just implement the quicksort logic. But again, there will be some restriction to use this because it is much simpler, right? So here you are not applying some bigger logic here. So it is just left and right you are sorting and mid you are finding. And based on that mid element, you are again going left and right. So this is the most efficient one actually, but there will be restriction to use it in some portals. Don't use list comprehension, they might mention, or they might mention use this particular over partition scheme only. Okay, so you have to know these things, right? So moving on to the merge sort. So obviously merge sort is also, you might have already learned it. So what is a merge sort technique? Same like here what we have done. First we will find the mid position. Once we find the mid position, left half we have to sort separately. Right side, right half we have to sort separately. Then once we divide them into separate halves, we have to then remerge them. Once we reach the single element, we have to do merge operation. So this green color cells will indicate the merge operation. So merging is simple and straightforward. So whichever element is lesser, that element will come first, and the remaining element will be copied later on, correct? So we will check if the left half is lesser than the right half, then in the one more array, we are going to copy this element first, or else this element first, right? So whichever is lesser, we are going to copy. Then like that, we have to keep on merging the elements, right? So this is the merge sort function, which you can try to implement. So I give it as a homework for you people because we have to still see stack and queue. So can you try to do this or you want me to explain this one? So it is like exactly same like your C language, whatever you have done, but I'll just give you the clue how you can divide it. Suppose if you have merge sort function, which takes array as the input, right? So same condition you have to apply. The base case is if the length of the array is greater than 1, ulta, right? So there it is less than 1. Here we have to check for greater than 1. Why greater than 1? We have to keep on dividing the array until the array is greater than 1, right? So once it is reached 1, we have to stop dividing. So if the length of the array is greater than 1, we have to find out the mid position. So for mid position again, find the length of the array, then divide by 2. So you'll get the mid position. Then once you get the mid position, left side of the array, you can sort it separately. So what you can do, you can using the slicing concept, you can extract left part. Similarly, right part, how will you extract? From mid to the end, right? So using slicing, what we are doing, left part we are extracting up to mid, A of print, and right part from mid to end. So we get two halves of the array like this. This is left and this is right as per the mid position. So once we get this part, again we have to keep on dividing, right? So we have to again call the merge sort function with the left half, then merge sort function, with right of, because until we reach the length of the array less than 1, we have to keep on dividing into 1. So once it is uh, reached this condition, length of the array is not greater than 1, we have to just copy the index values from both the arrays. So initialize with all of them to 0, correct? Okay, what you can do, I comma j comma k equal to 0. So initialize all of them to 0. Then use while loop while while I is less than length of left array and j is less than length of right array. We have to merge, right? So this is a merge operation. So as long as your I and j are within the range of left half and right of the array, we have to keep on merging. So if left of I is less than right of I, right? So if left of I is right less than right of I, what you have to do? Copy the elements into one more array. For example, take result, right? So result of k equal to left of I. Then you have to increment the I value because you have moved the left side of the array. If this condition is false, what you have to do? Copy the copy the right side of the array, that is right side of j. Both the pointers are pointing to left and right point. I is pointing to the left array, j is pointing to the right array. So once this is done, you have to increment k value. K value because we are combining them into the different array, right? So k is keeping track of this combining array, whereas I is keeping track of left array, the j is keeping track of right array. Then the combining arrays, k will be keeping track of it. So this is the one thing which you can do. So once this process is done, if there are any remaining elements, so if suppose if there are some more elements left with left part of the array and right part of the array, you have to just merge them together. So you can just complete this logic later on. So this is not that difficult, but again, I will add one more test case here. You need to print the output after each merge, not the final output. So can you tell me what should be the order in the output? What I'm asking in the test case is we have to print the output after each merge. Once you keep dividing, finally, once you reach the single element, you will merge, right? So what is the first elements that will be merged? So the order of the output will be first 3, 7, correct? Then 2, 16, then 2, 3, 7, 16, then 4, 24, 9, 11, then 4, 9, 11, 4. So hope you're understanding what I'm expecting in the test case. So after each merging, you have to print what is the output at that particular point. So output will be like this. The order I'm going to write here. So first, second, third, fourth, fifth, sixth, and final seventh. So you have to print all these outputs, not just the sorted array, right? So in your test cases, you have to make sure you are going to implement this logic, right? So print after each partition, each merging, right? So 3, 7 are merged, so you have to print that. 2, 16 are merged, you have to print that. Then you are going to merge 3, 7, 2, 16. This is the third output. Once left side is completed, the right side will be merged, right? So 4, 24, 9, 11, 4, 9, 11, 24. Then once these two are merged, final this left array and the right sub array are going to be merged. So this is our order of the output which you need to follow. Okay. So what is the logic or where you need to add that in between merging point? You can just try to practice and implement. Okay. So this is the merge sort which you need to remember. So hope you understood. I'm not explaining in detail, but hope you can the remaining logic we can complete it. Right. So next we have stack concept which you need to know. Right. Stack and queues. So I will explain stack concept. Queue, you can just follow it up because it is same as the implementation of stack. But what are the methods that are supported, which you can explore later on. Fine. So there are multiple ways to implement stack and queue in Python. So I'll list it down first. Uh, like now, since you are in first year, I'll give you two approaches. Once you go to a higher semester, you can learn all the approaches. So one is using list as stack. Second one is using uh, collection framework called as DQ. So DQ is the inbuilt library which supports both stack and queue. You can implement both stack and queue using this single library. Then another is using custom class. Okay, custom class. So these are the three approaches which you can use for implementing stack and queue. Custom class means you require the knowledge about OOPS, right? OOPS concept. That means class and object, right? So as of now, you need not to worry about this. What is class and object? When you are going to second year, you will be learning OOPS concepts in Java. Same thing you can later on learn in Python also. So custom class, you can do it later on. It's not mandatory to learn as of now, but those who are interested, they can explore what is class and object, how to create our own classes, right? So that is three approaches are there. So what is the best implementation of stack is using DQ. Okay, this is using list. So which one we have to do in real time is people use DQ only because it is for larger data set. DQ is more efficient because internal representation of DQ means it is double-ended queue. Double-ended queue means it is having double-ended pointer pointers. Basically, you can call it as a doubly linked list also. That means every values are connected by the pointer, not like a array. So internally, the searching, inserting, deleting operation will be very fast because everything is accessed using pointer. So it doesn't take more time to find what element to delete or where to insert the element, right? So it will directly access the pointer and insert the element. So it doesn't need to modify the stack also. So that's why DQ is more efficient compared to all the approaches. So you have to remember this point. So which method we have to use for implementing stack and queue in Python is using DQ collection framework. Okay. So what is the reason? The reason being its insertion and deletion process is much faster compared to the normal arrays because of the two pointers, right? Suppose if you are trying to delete the stack which is present in the last position, so your DQ will not iterate the stack from the first position. Directly, it will start looking the element both from the first as well as the last, like quick sort, which we saw I and J. So wherever it finds the element, suppose if it finds in the first pointer, it will delete it. If it finds in the second pointer, it will delete it. So since from both the sides, it is looking for the element to delete, the number of iterations will be less, correct? So that's why DQ is very fast compared to the normal list. So this is a very important interview question. Why we have to use DQ? Why there are so many approaches? Which one is best? What one to learn? So you should know the difference between these approaches. Okay. So how to use this DQ to create the stack is the next question. Okay. So the library file, how to import is from collections, import DQ. So collection is a framework which is available in Python library. And in these collections, we have a library called as DQ. So this is the complete syntax. So always you have to use this first. From collections, import DQ. Okay. Then how to create stack using DQs. You can create any variable name. So I'm naming it as stack only. You can create your own name also. So the name of the stack is stack itself. Then we have to create the object of DQ. See, this is creation of the object of DQ. So stack equal to DQ means we are creating a stack using this DQ function. Okay. Once we create this, all the library files that are available in this DQ, I can access from this object, stack object. Okay. Now, suppose if I want to insert element into the stack, I have to just use the object name stack dot append. There is append function which is inbuilt in the DQ. So I'll just pass the values in stack dot append of 30 or 40, stack dot append of 10, right? So I've added three elements. Now let's see how to print the elements. So if I print that stack, so what is the answer I'm getting? 20, 40, 10, right? So 20, 40, 10 is what I'm getting. DQ is coming in by default. So if you want to avoid that, you can convert that into list. Okay. So now you are getting the output as 20, 40, 10, right? So append option by default, append inserts the element in the end, right? So this is the stack that we have implemented. So obviously, 20 is the first element, 0, 40 is the second element, which is 1, then 10 is the third element, which is 2. So obviously, we are implementing it like a stack framework only, right? So the last element which we insert will be the first element that is going to be deleted. So we call it as a LIFO, last in, first out. Okay. So in that order, the elements are displayed. Now, suppose if I want to delete the element, what you have to do? Suppose DE or we are equal to stack dot pop. We can use pop function, which is available inbuilt again. So what does this pop function do? So let's print that we are okay. So which element got deleted? The last element got deleted, right? So that is we are following the principle of stack, where like the last inserted element has to be deleted first. So inbuilt pop function is going to do that task for us, right? Stack dot pop will delete the last element, right? So similarly, if I want to access the topmost element, right? We call it as a peak element. So peak element, how can I access? Stack of -1. So this is like using slicing what we have done. Correct. So at this point, the elements that are left is only 10 and 40, sorry, 20 and 40. So peak element, I'm getting it as 40 because that is the next element in the order, right? So peak elements means the topmost element. Then similarly, if you want to check whether the stack is empty or not, you can just mention if not stack. So if not stack means we are checking whether it is empty or not. So print stack is empty, else print stack is not empty. Okay. So what is the answer we are getting? Stack is not empty because there are two more elements in the stack. Right. Along with this, stack also has a lot of library files which you can use. Like for example, you can count. So stack dot count of 40. Correct. That means how many times that 40 is there in the stack. So we are getting the answer as 1 because only one time it has appeared. Similarly, you can reverse the stack dot reverse, right? So you can just print the stack, right? So you see the stack is reversed. So these are all the supported library files in the stack, right? So you can implement using DQ. That is one option. But generally, you should know both the approaches. One is using custom class and one is using stack. Okay. So now I am going to create a custom class using, I'm not custom class using list stack built-in. This is the using DQ which you can implement. But generally in interview, they will ask, don't use DQ, create your own class. So like for that, you have to use this custom class, which you will learn later. But the first approach you should know how to use list and create it as a stack, right? So stack using list. We are going to implement that one now. So you just create an empty stack with the list. So like list itself, we are using like it is behaving like a stack, right? So you know what are the stack operations? Can you tell me what are the stack operations? Push operation, which will receive an element or an item, we call it as, right? So what we have to do, push will no read an element from the user item, then that has to be appended into the stack, right? So stack dot append item, correct? So we are appending the elements into the stack. If you want to print customized message, you can say element inserted into the stack. For example, print what is the element that user has passed, and that element you can mention. So f of item inserted into the stack. Okay, this is push operation. So you are creating a separate function for that. So similarly for pop operation, we need not to take any input. Before deleting, what we should make sure? Tell me. Before deleting the element from the stack, what we should make sure? Whether stack is empty or not, correct? We can't delete without checking the stack is empty or not. So we have to check if not stack, correct or not. This is the syntax I told you. If not stack means print stack is empty, cannot delete. Right, can't delete. Then you can return none. I'll tell you why we are returning none. None means nothing to delete. If suppose if there is element to delete means we are going to return. Tell me what is the syntax I have to return. How will you pop? Just now explain. What is the syntax? Stack dot pop, right? Return stack dot pop. So this will do the delete operation. Similarly, display. So display operation. What we have to check again? Same condition. Before displaying, we have to check if the stack is empty or not. So same condition you can use here. If the stack is empty, we have to, if not stack, we have to print stack is empty, but we can't return. Instead of return, what you have to do? Else case. So else what we have to print? Stack elements are. So we have to print that stack using star stack. Why I am using star stack without comma? So it will unpack the values. Right. So star stack is the one which will print the elements. Now we have to implement menu driven application, right? So that is the concept. Always stack and queue should be implemented as a menu driven application. That means based on the menu, user has to take the decision. So we have created these many functions. So I told you you can use infinite loop, right? What is the infinite loop? While true. You can create while true. That means it will keep on looping as long as there is an exit condition, right? Then you can print the menu options. So we can call it as stack menu. Then slash t. First one is what? Push. Then slash t. Second one is pop. Slash t. That space I'm giving. Then display. Then last one is exit, right? So we have to exit from the loop if we are done with the printing, right? Then once this is done, what we have to ask the user? Tell me. We have to ask for the choice, right? So for user, we have to ask the input choice. So int of input. So whatever the choice the user has enters, that choice, based on that choice, we have to take the action. Tell me next what we have to do. If choice equal to 1, right? See here we don't have cases, right? So if choice equal to 1, what is that we have to do? I'm using if else if. So if choice is 1, we need to enter the elements to insert, right? You can take one variable item equal to int of input, correct? So that element we have to insert into the stack means we have to call the function. What is a insert function? Push. So push of item. So we are going to call that function. So no need of break statement in this case because we are using if else if. So if the choice is not 1, else if choice is 2, what we have to do? We have to call the pop function, right? And since it is returning the element, we have to store it in some variable, result variable. So we have to just check if result is not none. Now you understand why I'm returning none. So if result is not none, then we will print what element it got deleted. So if deleted element is, correct. So what you have to print, whatever the result we got. only if it is not none. Otherwise, it will print none, correct? Then same thing we have to do for display. Else if choice equal to 3, just display the stack element. Thing to do here. Finally, else if choice equal to 4, what do you have to do? Break the loop, because we have to come out of this infinite loop, right? So at this point, we have to break the loop. One more condition you can add. Final condition, else printf, not printf, print invalid choice. Correct? So based on these conditions, we can try to implement. So 4 choices we have, and if anything else the user enters, again repeatedly we have to ask him to enter the valid choice. Okay, so you see, this is our stack menu. So push, pop, display, exit, right? Okay, so one I will enter. It is waiting for me to enter the element. So what is the message I got? 34 inserted into the stack, because that is what we have customized here. Then similarly, I will enter 1 again. 56, 1, 78. Okay, so let's try to display. So what are our stack elements? 34, 56, 78. Right. So you see in the order only, last element which we inserted, it comes at the top. Suppose if I want to delete 2, so deleted element is 78. Topmost element got deleted. Okay, that's something. Okay. So display, delete. So deleted element is 78. Again delete, again delete. So at this point, what I'm getting, stack is empty, cannot delete. Correct? So because all the elements are deleted. So similarly, if I display, I'm also getting stack is empty. So this is stack application using list. Okay. So normal list we are using and creating the, shouldn't we reverse? That is like internal implementation is like that only. So maybe for your understanding, you can reverse it. But internally, 78 means that is the topmost element. For example, how you are inserting 34, 56, 78. Maybe while displaying, you want to display 78, right? So 78, 56, 34. So for your understanding purpose, you can reverse it and display in that order. But generally, internally, they are stored in this order only. So there is no need to reverse it and print in general. But generally in your, I think in your syllabus, you might be printing them in the reverse order, correct? So 78, 56, and 34 you might be printing. So if that is the case, you can just modify the display function. So what you can do, just reverse of tag you can do, then you can print it. Not necessary. Okay, so this is the stack concept, which you can do it using menu driven application. So make sure you implement it with the given approach. As I told you, using DQ function also you can do. This is much easier. But using list also, you feel like there is no much difference. Same implementation only. But we have created a separate functions to do that menu driven application. Similarly, you have a queue also, which you can do it. So give me 5 to 10 minutes. So we will just see what is queue also and what are the function it supports. So basically queue I will explain and based on that you can try to implement these things in the model. So up to merging I have added. By tomorrow I will add this stack and queue, because test cases I am making based on test cases we should be able to do it. Okay. So similarly you have a queue, right? Using collection framework from collection import DQ. So don't get confused. DQ means it will only implement queue. DQ is a generalized library name. using DQ, you can implement both stack as well as queue. Okay. So suppose if they say, suppose queue name is queue itself, queue equal to, you can also initialize empty DQ, or you can mention compile time values. For example, I'll mention some values. So here you are not creating empty stack or empty queue. You are mentioning some default values. Okay. So now DQ dot append I'll do. DQ dot append. Suppose 6 I am appending. Print DQ. Okay, not DQ. What is our name? Name of the queue is queue, right? Okay, where the element is added? The element is added in the right hand side. So that is the principle of queue, right? So front and rear pointer you have. That means element should be inserted at the rear pointer and element should be deleted from the front pointer, right? So by default, that means whatever the element that I'm adding, that should be added in the front pointer. So in this case, by default, it is adding in the left side. But is it correct, or should we change some approach? Generally, how the queue works? Suppose you are having inserting in empty elements, both in F and R will be initially 0, -1. So when you insert the first element, R will be incremented to 0. Then F will be incremented to 0. The next element when you insert, first you will increment the R, then you insert the element, right? So 20 R, then 30 R, 40 R, correct? So basically only the rear pointer is moving, the front pointer is remains same, right? So by default append means you will be inserting on the right side. Suppose say I will say q dot append left. So q has this append left function. So where did we insert? So we inserted on the left side of the array. I mean the starting from the front. So it supports both insertion. You can insert from the front end also. You can insert from the rear end also, right? So append left will insert on the left side. Append will insert by default on the right side. So similarly, for deleting, what you have to do, suppose I want to delete some element. So as you already know, if I say pop, which element will get deleted? By default, the right side element gets deleted. But this is not correct, right? This is not following the principle of queue, because what we say in queue, the front element should be deleted first, right? So by default, q dot pop means the last element is getting deleted. So to overcome this, what you can do, uh, you have one more function for this. So result equal to, no need to use result. Directly you can write q dot pop left, right? What do you have to use? Pop left. Then you can print the queue. So now you can see what happened. 100 got deleted. So you understood now, to follow the principle of queue, what function you have to use? For stack, what function we have to use? For deletion, normal pop we have to use. For queue, what function we have to use? Tell me. If you want to follow the principle of queue, for deletion, instead of just pop, you have to use pop left. Okay. Then only we'll be following that principle of queue. For insertion, append only you can use. For deletion, you have to use pop left. Okay. Please remember this thing. So when you want to create a menu driven application for queue, or rest of the things, everything remains same except this pop, right? So here you have to make pop left. Remaining all is similar to queue only. I mean, it's similar to stack only. Similarly, if you want to, there are few more library files supported by queue. Queue dot extend you can do. You can extend all together new elements. So this 743 we have extended into the right side by default. But again, you want to insert multiple elements on the right side. I mean the left side. Right? So you can see we inserted multiple elements on the left side at a time. So this extend and extend left are supported. All these are supported because of DQ library. So without this, you can't do this, right? So DQ is very powerful. So similarly, if I want to do some more operations, can you observe what happened? So elements are rotated by two positions. So you see initially 300, 100, 200, 300 were here. They are rotated twice actually. So rotation also you can do on the queue, right? Apart from like printing it. So similarly, you can do the reverse also. Somebody asked, right? So reverse is mandatory for few applications. So you can use the reverse, right? So you have reversed the element from left to right. So these are the basic like most important operations in queue. So up and left you have to use if you want to insert from the front end, just append. If you want to insert from the right side, pop left if you want to delete from the front end. So these are the important queue functions. So what you need to practice is convert this, you know, operations into menu driven application, like just what I have done here. Based on that, try to match the test cases. Okay. So I will add these questions by tomorrow, or maybe like not by morning, maybe by evening. So by today, you practice today. You can practice quick sort and merge sort. I have added two programs. By tomorrow evening, you'll be added all this program stack, queue, and remaining questions, right? So try to practice this question. Definitely, I'll try to give these questions in your assessment, at least one of them. So there will be one question from stack, one question from sorting, right? So make sure practice all the insert, searching, sorting, and as well as stack and queue programs, whatever I'm going to add. So those who have practiced, it will be easy for you to implement. Otherwise, these things are a bit, we require practice for this. Okay. Any doubt you have? So hope whatever the session we have covered till now was something beneficial for you guys in terms of like basic preparation of Python. So we will continue these sessions into one. Maybe we will start with Java, right? So you might have learned Python now. Into one, we are planning for Java no sessions. So we will see when we can start. But I think up to this, it's more than enough for preparing for the product batch. So whatever we have taught, just practice, revise. Foundation is very important. That's why I always teach everything from the syntax. So something you might have learned, at least like out of these many sessions, at least 30-40% might have gone to your head and you might have improved. I hope so. So maybe it is not like 100%, but at least 30% should have been gone to your head. So hope you enjoyed the sessions as much as I did. Maybe those who have definitely learned something, they will be benefited. Okay. So anything that you want to share? Was sessions were okay? Was it beneficial or is it like some revision? Yeah. So anyone wants to give any kind of suggestion or feedback? Any feedback? Like too difficult, too many questions, too much torture by me. So many questions I have made you practice, right? So anyway, I will add. I'll come personally and meet you guys before the assessment, and I'll take personal feedback also. So anything positive, negative, like try to share to me. Definitely, we will try to improve it for your juniors. Okay. So, sir, will you upload the recorded class? Yeah, all are already uploaded. I think you were not aware of that. Maybe YouTube, right? So I think up to bit manipulation I've already added. So two more videos I have to add. By tomorrow I will add. Okay. So okay. If you guys are benefited, then I'm very much happy. And as you know, I put a lot of effort on doing all these videos, formatting, uploading, and these are definitely not helping you only. These videos are helping to your seniors also. So we are doing training for them now. They are in 2.2 and 3.1. They forgot all this basics of Python formatting, loops, list comprehension techniques. So they all are watching these videos. So by doing this is not only benefiting you guys, it is benefiting to all the students. So that is my focus. So those who have learned it, definitely they will be benefited. Formatting and single-handed all these questions, sometimes I am not adding questions, sometimes there is delay. The reason being, everything I have to do it alone. So all these programs, test cases, I have to write, sit and write. So it's not just one day work. So that's why there might be some delay whenever there was no question in the platform. But I made sure there are good questions that you need to practice, and I've tried my level best to give you the good content. Definitely in future, even I know there are a lot of things which we can improve in terms of assessment, in terms of implementation, in terms of class scheduling. So we will come up with some new plans for that for your juniors. But you guys are like first batch with whom we have tried this. Definitely will be benefited. So based on your feedback, your interest, and how much you learned, we will be able to take the further decisions. So by learning this thing, by attending, even like you guys have helped us also, because there are some around 200 students who are consistently practicing, consistently attending the online sessions, and never missed a single session. Also, I've seen such students. So definitely, such students are going to motivate us also to do the things in a better way. Okay. So we will meet you again during 2.1. We will definitely come and start Java sessions. So a lot of plannings we are doing for your batch. So be excited. Keep learning. Don't lose the coding consistency. That is my personal suggestion. By personally teaching to you guys, I have improved a lot, because I have to prepare for 2-3 days before. I have to learn what I have to teach. So my coding is increased. Level is increased. My typing speed is increased. Understanding error skills is increased. So don't think I am helping you guys. By teaching you guys, even I am getting some benefit, right? So it is mutual. So you have to think that positive mindset. So learning is always mutual, right? By sharing your knowledge, you are growing yourself also, you are making others also improve. So you have to do this. If anyone are not understanding, you can help them to understand. By teaching them, your knowledge will improve. Okay. Thank you very much. We will see in the session. Okay, it's already 8:20. Uh, okay, all the best for your assessment. For any doubts, any test case mistakes, please text me, no problem. I will correct it immediately. Okay, so see you soon. Thank you. Thank you, everyone.